Hello, everybody. Today I will be solving problem 6.7 from Griffith's E&M book, 4th edition. And so for this problem, we're looking at a infinitely long circular cylinder carrying a uniform magnetization M parallel to its axes. We're going to find the magnetic field due to M inside and outside the cylinder. And so I've drawn a configuration here, although this configuration shows a finite cylinder. We're just using it to visualize our infinitely long cylinder. And so I've aligned the M vector with the z hat direction. And so for the cylinder, we note that the normal vector points in the s hat or radial direction in cylindrical coordinates. And so one of the first things we can say about this problem is that since it carries a uniform magnetization M, we can say this M vector equals M z hat because it is uniform. And so next we want to find the bound currents to proceed with this problem. So the first one is the volume current of this configuration. And this is the curl of our M vector, and that'll be 0, because as we said earlier, this M magnetization is constant, so we expect no curl from that. And so the surface current is this vector KB equals our M vector crossed with the N hat direction. And so plugging in for the M vector crossed with the S hat, as we said earlier, our normal vector points in the radial direction S hat. And so in cylindrical coordinates, Z hat cross S hat is phi hat, or the circumferential direction. So we note here that our only bound current is the surface current. So then that means that we can treat this configuration as a solenoid because the current points in the phi hat direction. And so to better visualize this, I've drawn a configuration here where the currents, where we can think of this infinitely long cylinder as a solenoid with closely wounded coils, and here each the coils point, its current points in the phi hat direction. And so to proceed, we'll be using Ampere's law on this solenoid configuration. And so what I've drawn here is 2 Amperian loops to help solve this problem. Each loop has a width of L, and then its length is either S1 or S2. And we've chosen the current point in the direction that these arrows are pointing in that are drawn on the loops using the right-hand rule. So to proceed, we first need to think about what components the magnetic field will have. And so to first note that the magnetic field will only have a component in the z hat direction. And so this comes from the fact that first there will be no circumferential component or phi in the phi hat direction. So b phi will equal 0. And this is because the current is already pointing in the phi hat direction. And from the Biot-Savart law, our current crossed with the differential length that we choose in the phi hat direction will be parallel. And so that cross product will equal 0. And then there will be no radial component, so there will be no B S component. That'll be 0, because thinking about this problem, if we were to flip the direction of the current, this would imply flipping the B field. But we can achieve flipping the current by flipping the solenoid upside down, which will change the current direction, but that doesn't mean logically that the B field's component will direction will change. So that means that there can be no radial component for our magnetic field. So the only component left is BZ. And so we'll find that using Ampere's law. So to apply Ampere's law on the first loop, we first note that Ampere's law states that it is the closed integral of the magnetic field vector dotted with the infinitesimally small length vector we're choosing equals mu naught times the current enclosed. And so we have 4 different components for our loop here that we've chosen: this left, top, right, and bottom components to our loop. So we can break our integral into 4 different integrals. And so here, using the definition of the dot product, we can say that our integrals will be the magnitude of the magnetic field times dl cosine of the angle between them. And so we note that dl, at least for the left and right sides, their angle between them will be 90 degrees because we know B has to point in the z hat direction and dl will be pointing in the z hat direction. And so their angle will be 0 degrees. And that for the top and bottom portions of these loops, the angle between them will be 90 degrees as from the configuration. And so cosine of 90 is 0. So these 2 integrals will be 0. And then solving the remaining integrals, we have using S1 for the distance to the outside field. We have B inside times L, because the magnetic field for this portion will be different for the loop outside. So B inside times L plus B outside, and then to identify it, it'll be 1 because our loops are different lengths, S1 and S2, equals mu naught, and then I enclosed. And then just to separate out B outside, we do some mathematical algebra here. And so we get this equation right over here for B outside 1. And so the same steps follow for the second Amperian loop in green, where S2 is the length of that Amperian loop. And so then, now using S2 for distance of the second loop, B inside times L plus B outside 2L equals mu naught times the current enclosed. And B inside, it'll be the same for both equations. The magnetic field is inside the solenoid will be the same. And so doing as we did before, we separate, we want to isolate B outside. And so it equals to this equation, but if we note immediately, this also equals B outside 1. So from above right here, they both equal to the same thing. So that must mean that B outside is a constant value. And so further, some boundary conditions for this solenoid are that as B outside, as S tends to infinity, we expect the magnetic field to equal 0. And so because B outside is a constant, it must be 0 overall. So B outside equals 0. So that leaves us with the following equation: B inside times L equals mu naught the current times the current enclosed minus B outside L. And this comes from simply moving this to the other side. And so that will equal 0, as we just noted above. And so our equation then becomes B inside the magnetic field inside the solenoid equals mu naught times I enclosed over the width of our Amperian loop L. And so to note, KB is also can also be thought of as the derivative of I over the length, the dl, or di over dl, which is the length perpendicular to our current. And so solving this, I enclosed equals kb times dl, and that integral is just simply kb times L. And so we can substitute this back in here. So going back, B inside is mu naught times kb L over L. And so the L's cancel out. And then kb, as we noted from all the way above, kb is equal to m in the phi hat direction. So we're taking its magnitude here. So it'll simply be mu naught m. And so overall for this problem, B inside equals mu naught times m, and this is in the z hat direction as we've chosen for our problem, or it's pointing upwards. And then B outside is simply 0. And so I hope you enjoyed this solution, and thank you so much for listening.